Assalamu alaikum warahmatullahi ta'ala wabarakatuh. Bismillah ar-Rahman ar-Rahim. Ladies and gentlemen, let's continue our tutorials about computational fluid dynamics, CFD. In this video, we're gonna complete our turbo machinery simulations. In this video, we're gonna talk about the radial turbine simulation, static structural analysis. This is a very important thing after carrying out the CFD simulation and show the effect of the fluid dynamics on the blades and the rotor, stator, and the fluid using CFX, Fluent, or anything like this. Here we have to complete the project using the ANSYS mechanical procedure. But before we start, we have to take a look on the some references of the basics of the mechanics of materials. It's a very good reference that is available on Google search. Mechanics of Materials 6th edition. You will find everything you need about the basics of the stress analysis, strain, deformation, retention, compression, and shear, axial loaded members, torsion, stresses in beams, basic topics, stresses in beams, advanced topics, analysis of stress and strain, applications of plane stress, pressure vessels, beams, and combined loadings, deflections of beams is a very important topic, statically indeterminate beams and columns, view of solenoid and moments of inertia, and here the reference of historical notes. And the appendix, you'll find the very interesting reference, provides you with the basics. Okay. Also, there is another interesting reference is shows outline strength of materials. Also, it is available on Google. Solve problems. You will find the same topics, but you find here in short. You find the topics in short, and then after the chapter, you find the solved examples like this. Here there are solved examples after the equations. So it is a very good reference to refresh your information. Okay, so now we're gonna talk about ANSYS mechanical APTL structural analysis guide. Also, you can find anything related to the ANSYS mechanical user guide on Google. Here we have a project using Vista RTD. So this is the turbine. This the condition of the turbine. Okay, you can set it, and it's a random project actually, because we changed the rotational speed in the CFX and anything. And here is the 1D solution of the problem, and here are the velocity triangles. Okay, so then you can transfer this, create new geometry to see what are behind the scenes. Open the roller. Gentlemen, if you finish your CFX setup and open the solution and you get an error, update solution is error, so you have to clear generated data and reset the solution. and close ANSYS, and then go to the CFX directory file, and you have to open it from start menu. I'm gonna show you this, but please have patience until we this. Okay. Suppose here you open setup and you finish it, and then you open the solution, and you get after many iterations you stop the solution, but you get an error, update failed. So you have to reset the solution and clear the generated data. Okay, and you have to be sure that the setup is this right check mark is okay. So I have to close ANSYS and go to start menu and write CFX. CFX and open your CFX. And open CFX pre. Okay. Okay, and open the CFX file. You have to know the directory. You can click on the setup, and you have to know the directory name CFX or anything. You have to know where is the location of it. The project is radial turbine. Okay. Right here we go, CFX, and this is the file I need. So it's the same. It's as the same as clicking on this. So I'm gonna open CFX pre. Okay. Oh, I'm sorry. It's another project. So it's this is the last project that we talked about. No problem. This is the same file. If you open it from ANSYS or you do not open it, it's okay. Now you have just to define run and to save the run. After saving it, you will find the same method of input of the input, the number of processors, or the serial or parallel. Okay, and so on. You have to open the solution, and so it will be okay. Then you can stop the solution and carry out the backup file without any problem, and the solution will stop normally. Okay. Okay, out. Okay, here, okay, let's complete our topic. So here is the structural and static analysis. Static analysis calculates the effect of steady loading conditions on a structure while ignoring inertia and damping effects. So steady loading, it means that the loads do not change with time, and such as those caused by time varying loads. Here is while ignoring inertia and damping effects, that those caused by time varying loads. A static analysis can, however, include steady inertia loads such as gravity and rotational velocity, and time varying loads that can be approximated as static equivalent loads, such as the static equivalent wind and the seismic loads commonly defined in many building codes. So static analysis determines the displacement, stresses, strains, and forces in structures or components caused by loads that do not induce significant inertia or damping effects. Steady loading and response conditions are assumed. That is, the loads and the structure's response are assumed to vary slowly with respect to time. So the types of loading can be applied in a static include externally applied forces and pressures, steady state inertial forces such as gravity, rotational velocity, imposed non-zero displacements, temperatures for thermal strain, and fluences for nuclear swelling. Clear? Okay. And so on. Here, the linear and the non-linear static analysis can be either linear or non-linear. All types of non-linearities are allowed. Large deformations, plasticity, creep, stress, stiffening, contact elements, hyperelastic elements, and so on. So this chapter focuses on linear static analyses with brief references to non-linearities. Okay, you can read more about these simulations and how to use it, performing static analysis, apply loads, and all the things you need, and the static analysis here. And then you can see the model analysis. Okay, it is not a big story. Also, you can find here, this is one of the best videos. You can see it, this aeromechanical simulation of turbo machinery. This video shows the steps that you need to have a full turbo machinery project, beginning from the CFX, then transferring into the static analysis, static structural, then the model, and so on. Okay, so now close this and this, and close this. Okay, here we go. This is the these are the blades that we have. You can also suppress this body because we do not need it. Okay, here are the blades only, so you can add the if you see here the rotor of the radial turbine, rotor. We find here that it includes the shaft hole, okay, or something like this, and the round part that supports the blades. Okay, so these are the blades only. So for static structural analysis, you know that it is not necessary to find all these things here, because we have to only export the points for the CFX analysis. So you have to export the geometry in anywhere, and please export it as parasolid text xt. Okay, then you'll be able to open it from any CAD software. For me, I am interested in using Autodesk Inventor. But it is not compatible with transferring the file into a parcel again. So we have to after finishing our model, in Inventor, you have to open it using SolidWorks and re-export it, receive as solid file. Okay, you're gonna open the model. Turbo machinery. It was my friend Sophia project, so let's open it. My friend Sophia is from Jordan. We worked together to finish her graduation project, and she has successfully finished it. It was a very interesting project, but it was a CFX investigation only. Okay, here is the roller, but we add here the base or the round part and the shaft. This is the whole shaft. Okay, if we delete all these, okay, you'll find here. So this is the geometry exactly like this. Okay, but we add the drawings to it. Okay, we add this hollow shaft and this part to be ready for the investigation. So anyway, you have to prepare it for the static structural analysis. Okay. So after this, the rotor is ready for the investigation. The investigation only is carried out to investigate the blades, not the flow around the blades. CFX or Fluent or these solvers are interested in studying the behavior of the flow around the blades, but the static structural or mechanical is interested in investigating the investigation of the blades itself. So I do not need to generate the flow path here. We only need the realistic or the solid part. Okay, let's take a look on some papers here. The investigation here about the CFX, I think. Okay, and this is the CFD results. We showed this in the previous tutorials, and you can get this after finishing the solution. And the bleed loading, you can see it from the Russian tutorial that I mentioned it. And then the structural analysis results. Finite element analysis was conducted in order to assess the stress distribution for the turbine wheel. FEA was performed using ANSYS workbench. A static structural analysis was carried out. This is necessary because of the high rotational speed and high flow temperature experienced by the impeller. So the alloy Inconel 718 was selected because of its high quality mechanical properties under extreme temperatures. So it's very important to know that selecting the appropriate material will enhance the turbine's performance to ensure safe behavior under working conditions. The von Mises yield criterion and needs to be satisfied. So you have to know how to deal with the simulation. This criterion states that a material is said to start yielding when its von Mises stress reaches a critical value known as the yield strength. The yield strength is defined as the stress at which a material begins to deform plastically. Okay, and so on. Here are the properties of the material. Notice that the yield strength at 1172 megapascals is very high. It's very good at this temperature. Okay, so it can withstand the high conditions. And also you have to know the safety factor that you can reach or you need. And here is the statical structural, and here is the rotor geometry exactly like this. Okay, and so on. You will find here the mesh, and the this is the equivalent von Mises stress, the minimum and maximum in megapascals, and also the stress here. Okay, and here is the total deformation as a result of the temperature and the pressure distribution. Okay, notice that the deflection, the total deformation in millimeters, and the maximum is 0.07. So this is the predicted values. I think this is the safe values. And here the mesh is used if it contains these nodes and elements. A view of the mesh and rotational speed. Notice that you have to apply the rotational speed and which is the design point speed as a safety practice for an off design case. Also cylindrical support fixing radial, tangential and axial movements. The threaded hole is attached to the shaft that was applied to simulate conditions to account for the thermal expansion. A constant thermal load of 730 Celsius was applied. So you have to know that you can apply these conditions in the ANSYS structural analysis and get the results. So now we have to open the static structural, make a new project. Okay, first of all you have to check out the engineering data to set the material you need. Here the default is structural steel. I'm gonna use it to see its effect, and here is the properties that you wanna add. If you wanna add anything, you can just make this to add it. Okay, here the structure steel, and here the information that will be used, the tensile yield strength of it, and everything you need is here. And according to this data, ANSYS are gonna use it for the calculations. Okay, to add a new material, you have just type it cast iron. Okay, and to add the density, just make this and add anything you need and put the value, and here the unit. Be careful please of the units. Okay, but we do not need the cast iron now. I showed this in the tutorial of my tutorial about the PV photovoltaic cell cooling. Okay, let's close this. So let's open the geometry to import this. After finishing here, you have to export it as CAD format. okay, as a parasolid xt file. So parasolid xt file, then please open it using SolidWorks and resave it as parasolid xt, and then open ANSYS import external geometry. Okay, here is the this is the inventor file, and okay, I do not find it, so please, we're gonna make it. Export, scat format, save it on desktop. Okay, save. Okay, sorry. Here is DWG. I don't need it. DWG. Export, cat format, and the desktop, and parasolid xt. Okay, save it. Okay. Open SolidWorks. Let's try it as xt, but it does not work with. I think I did it before, but okay, that's why. I think you have to open SolidWorks. Okay, and file open our file, and here you can investigate the or check out the file. You'll have to fix any problem with it. If there are gaps or any problem with the part. Yes. Do you wish to run import the diagnostics on this part? Yes. Okay. Here there is a problem with this, so you have to open and attempt to heal all. Okay, face. Okay, now we do not have any problems. No. Then just save it as parasolid xt and replace it. Okay, now we do not need SolidWorks. Okay, go and here file import external geometry, and this at frozen or material thing does not matter, because we're gonna investigate this this part only. So click generate. And here is the magic of SolidWorks. We have here the roller. It's okay. Here are the bodies, all of it, all of them are solid. Okay, nothing more. Close this. And now we have to open mesh. Also here you can check out the basics from YouTube, the fatigue, and we're gonna talk about this later in the next couple minutes. Here we have to check out these videos about the basics. Are very interesting videos, learn engineering, and there are many videos about it. The fatigue failure analysis due to the repeated loads. Okay, here we go. This is the part. This is the mechanical part. Okay, here we go. Here is the mesh. Please, before anything, you have to check that all the geometry is right check mark. Okay, and there is no any question mark here. If you find any question mark, you have to re-import the model or make it in a way to that ANSYS does not face any problem with it. So here is the sizing for the sizing, and you have to know what is the appropriate size. The Y plus, like this thesis, ANSYS mechanical to determine the load and deflection. Static structural analysis is convenient. Mechanical is used to simulate the structural behavior, and the subprogram static structural is used. Okay, we're gonna you have to here, this is the property, and here is the you have to know the Y plus for the mesh you will use. Okay, so for this tutorial I'm not gonna show the details, you have to do it by yourself. So we're gonna use this fine mesh, right click and generate mesh. And here is the mesh. You can decrease or make it smaller, of course. Please do not follow my mesh. This is a random mesh. It is not based on any calculation. You have to calculate the Y plus and make it to know exactly what is the first layer thickness and this and these things. And you can decrease the size from here. Element size, can make it smaller than this. Okay, so here the analysis settings, the number of steps, can make it 1, 10 or anything, but it is not a function of time. So leave the seconds one, and we have to insert our loads. So we're gonna use the rotational velocity. Okay, before this, we're gonna have to take a look on this amazing paper in International Journal of Mechanical Engineering and Technology. You'll find this paper available on academia. So this is academia. Here is academia. Please show research. I found it in academia. You have to get the papers from academia. You have to log in using your Facebook or Google Drive. Okay, you'll find it here. Just type in Google the title, and you're gonna get it. Okay. So here is a CFD simulation on the rotor, this turbine. So this turbine, this is the rotor and the nozzle and the draft tube, and this is the casing or the volute. Okay, so this is the CFD mesh for the CFD investigation, and here are the results, exactly like what we did in the last tutorials, in the previous tutorials. And here are the efficiency, theoretical, and CFD. They did not carry out experiments. Okay, and here we go, the structural simulation of runner in the mesh type and the element size, mapped phase tetra hadrons, physical, mechanical, not CFD. And here's the mesh, like this. And here the assumption number of R per S is constant. Here the RPM. So we have here to add the rotational velocity. It is around here 85 RPM multiplied by 2 multiplied by pi divided by 60 is 890.1.7 radian per second. Okay, and the axis is x-axis, and you have to know the revolution per minute. Make it minus. If you make it minus, you will find it clockwise, but you need it according to the realistic model. Okay, here is anti-clockwise. And here is the axis. Axis is Z. Exactly like this. Linear analysis is being done, not nonlinear. Static structure analysis being done. The model taken is Gerber 0 based. And here the boundary condition applied. Pressure on blade face is this 57380 pascals, and the environmental temperature is 22. So this is not a temperature investigation. And here is the notice that you have fixed support, the shaft place, and the pressure on this. Okay, and here's the rotational velocity. So we're gonna apply this. So the support is the fixed support. You have to know exactly which is the fixed support. I'm gonna select this, these faces. It's just an approximation. Apply. So it is the fixed support, like this, and the pressure. So this is a constant pressure, and it is uniform. Loads, pressure. I'm gonna choose the faces. Of only the blades, Please select the blades carefully. These faces, please select all the faces that you expect that they are subjected to the forces or the pressure. And this face. Okay, and unselect this. Okay. Okay, here we go. All the blades are green, and this part. Okay, here are the 55 faces, and here are the magnitude of the pressure. You can make it exactly like this, 57380, 57380 in the megapascals. 5738. Yes. Okay. So here is the pressure, it's constant, and all the blades are subject to this constant pressure. Okay, and the environmental temperature is 20. You can add it, or you may not add it. The thermal condition, yes. Also gonna make the same thing. And here. Okay, you can select all the blades or anything here. It doesn't matter. So because they are on the same temperature, 22. Okay, it's okay now. Here are our boundary conditions, and here are the results. The results, what we have here, the stress equivalent von Mises. So in the solution, insert the stress von Mises. Also, we can get the total deformation. Insert deformation, total deformation. Also, the fatigue. German here is Academy. You can log in using your Facebook and you will get anything you need. So the fatigue due to the loads, repeated loads. Insert fatigue 2. Fatigue 2. Okay, I'm sorry. I'll save the project. I closed it and reopen it, and then insert the fatigue tool. And use the fatigue tool, insert life and damage and safety factor. Okay, what is this? So the fatigue life plot said that if the loading is of constant amplitude type, then the result from life represents the number of cycles till which their structure can withstand until it will fail due to fatigue. So from the above plot, we can see that the structure will withstand up till maximum cycles. And this is the life. This is 1 to the power 6. And here fatigue damage is a contour plot of the fatigue damage at a given design life. Fatigue damage is defined as the design life divided by the available life. For fatigue damage, values greater than 1 indicate failure. Okay, values for here for fatigue damage, yes, values greater than 1 indicate failure before the design life is reached. In the preset scenario, it can be seen that the damage values are less than 1, so the structure will not undergo fatigue damage. Okay. So, gentlemen, you have to know that you can, if your rotor exceeds the number of cycles, it will fail. Okay, you have to know this, and you have to know that the design life. You have to know the design life and the available life. If this I think that you are not allowed to exceed the available life, because this is the maximum limit, I think. So it has to be less than 1 to be safe. Okay, so here is the safety factor. Here life damage and the safety factor. What is the safety factor? Fatigue safety factor is a contour plot of the factor of safety with respect to the fatigue failure at a given design life. For fatigue safety factor values less than 1 indicate failure before the design life is reached. In present case, region below 1 does not exist, so factor of safety is maximum for this case, so it's okay for this. If you see here any red regions, it is not okay at all. It will break, I think. Okay, so here is the safety factor, and these are what we have. So after this, solve. And please do not interrupt the solution or don't stop the solution. The solution does not take many times or several times or several minutes. Okay, but I'm gonna pause it, please. Okay, now, gentlemen, the solution is finished, so we have to check out the equivalent stress. You find here the equivalent stress. Note that we have here structural steel. Okay, structural steel. So this is in megapascals. So here the stress, and you can see when it changes. Notice the deformation here. So this is the expansion. Okay, so this is the maximum. It's very high, actually. It's very high. Okay, also the total deformation. So the deformation also is 0.01 millimeters. Like I said, it is the deformation is 0.007, 0.009 or 8 as maximum millimeters. So I think there's a very high deformation because the structural steel cannot withstand these loads. Notice here the deformation. So it is very bad to apply these loads on the structural steel turbine. And also, if we make the thermal condition more than 22 Celsius, maybe 400 Celsius, we will get it worse. Okay, and let's see the fatigue life. The fatigue life here is the maximum is 1E6. So here the number of cycles here. So all the blade here or all the rotor can. So the fatigue close state if the loading is a constant absolute type, then the result from life represents the number of cycles. Okay, so notice here that not all the blades have the same thing. This is the number of cycles. Okay, also this is the simulation, and here is the damage. Okay, so this is the life, and here is the damage, and you have to know the life design cycles. You have to be sure of these things. You have to know what is the number of cycles, the maximum. Okay, and divide the design life by the available life to know if this material will face problems or not. Okay, so here is the damage, and here is the safety factor. So this is the safety factor. I think it tells everything. We have many locations or many areas that the safety factor is lower than 1, so this is not good. So this tells you that this rotor will not fail because it is a very weak material. It's a very weak material. Notice. Okay, so here it is lower than 0. Here is the maximum, so it is very good material for this load, and here is a very wrong to use structural steel. Also, what if you wanna add anything to stress tool, more column stress tool to see the safety factor? Evaluate our results. You will not. You will get the result in the time immediately. Okay, this is the safety factor. This is safety factor of the fatigue, and this is the safety factor of the stress tool. I think it's related to notice that it is you have to tell ANSYS what is the limit you wanna make it as a reference. So I think this is made as tensile yield to tell ANSYS that your reference or the maximum point is the yield. If the loads are higher than the yield, the safety factor will be less than 1, as we see here. So this material is durable and cannot withstand this load. Also, you can make the thermal condition 5 Celsius and see what will happen. Solve, and you have to have patience again. Okay, Okay, we have here the results, and here the stress. Okay, at 500 Celsius, you'll find here the equivalent stress. It changes, and here the total deformation increases due to the thermal expansion. Okay, and here the life damage and the safety factor, and here the safety factor. Okay, save the project, please. Okay, and close it. So, gentlemen, this is the static structure for the rotor. Now we have to check out the stator. So make static structural again. So here is the stator. Also we have here the stator nozzle. This is the stator nozzle, but in ANSYS we only have the blade. Yes, the same thing. You have to export it and open it in any CAD modeling software, and we added this part. We carried out the circular pattern, okay, to be like this. The stator here. So this is the stator, and to carry out the same thing, the structural, the same material. Okay, please check out my PV cooling simulation to know more about the materials and adding them. So we have here import external geometry. And here the nozzle structural. Okay, this is the part. Close, open the model mesh. Okay, here the mesh sizing. Also have to check out the Y plus and the size, the appropriate size. Please do not follow my size. And here we go. So this is the mesh. It's a coarse mesh, still coarse, and the okay, it may work. And here I'm gonna insert the pressure also, and the supports the ports, I think. So the fixed support, you have to select the fixed support according to the test rig. We're gonna use this as a fixed support as an approximation for the model. Notice here that here the pressure in the at this and the fixed support. Okay, it doesn't matter, you have to be careful when you choose the static, the fixed support. We're gonna add pressure, and this is a fixed part, so there is no any rotational speed. The pressure, I'm gonna select this, and we're gonna uncheck the, we only select the blades, all the faces of the blades. Okay, have to be sure that you selected the required faces, and then select this. Now the pressure is applied on the blades. Okay, and here also 36490 6490 megapascal. 3649 megapascal. Also you can add temperature. Okay, it's okay to select them. 22 Celsius, so pressure and thermal, and also insert anything you need. Deformation, fatigue, stress equivalent, stress here, and fatigue 2, life, damage, and safety factor. Just hit solve, and anything you want to need, you can add it and evaluate all results immediately. So we have here the total deformation. Jesus. Notice that the total deformation in millimeter is very small. Okay. So this is the deformation. Just after 1 second, but it's a steady state. Okay. So this is the deformation in millimeter, and here the equivalent stress. Here the pressure, megapascal. Okay. Okay, and here the life. Notice that it's good. Here in megapascal, this is the stress. So this is the equivalent stress. Here is very low. Yeah. Here is 0.1 and 1 as maximum. So according to the material, gentlemen, of course, and here the life. This is the life. Okay, now, gentlemen, if you wanna apply pressure, but it is not uniform, or the pressure distribution is not uniform, so here, one-way fluid structure interaction is used to apply the pressure fluctuations to the blades. The pressure from the solution from CFX is imported from the static case to mechanical. All programs share a single geometry created with design modeler. The boundary conditions on the stator are set as fixed on the hub and shroud, but only the hub for the rotor, as it is able to rotate. As like I said, you have to know which rotating parts and which the parts are fixed. Centrifugal forces are dominating over the pressure forces and are included in the rotor blades by the rotational speed of the turbine. The pressure is mapped on the CFD surface. The geometry has to be selected as well as the CFD surface, which is transferred from CFX using linear interpolation. Mechanical nodal values are calculated from the CFD nodes. The mapping is not always successful, but the linear interpolation tolerance can be changed in CFX. This tolerance controls variable interpolation accuracy on or near boundary surface. So after finishing the CFX, this means what? All these things means that if you wanna apply pressure, but this pressure is not constant, or is it is not like this condition, means that you wanna apply pressure, but this pressure surrounds the blades are not. It's not a constant. So let's open the results from the CFX to know exactly what's going on now. I think that there are two methods. I'm gonna show you now the first method. Okay, here is the temperature distribution of the blade. We're gonna make it pressure to see on the blade. This is the rotor blade. Okay, and here we go. We mean here that we're gonna apply this pressure distribution along the blade as a result of the CFD analysis to check out the effect of this pressure distribution on the blade. Okay, so in other words, the pressure here is not one number. No, it is a distribution, and we need all this pressure. So what we have to do is to close this and get static structural, no static structural. And this is the engineering data. You have to know the material. Also, you have to get the rotor. And file, import geometry, and get the rotor. Yes. Okay. Before this, you have to make this method, get the solution and share it into with the setup. So open the model, starting mechanical. Gentlemen, please, you have to check out the tutorials, the basic tutorials of the static structural analysis, the simple tutorials to know how to deal with the software and how to get the results, how to make charts. Okay, like ANSYS nonlinear stress. This video for Dr. RADIAL. Please, gentlemen, subscribe to Dr. Delio channel to get everything he does. It's a very amazing channel. Thank you, sir. You are very helpful and your videos are very informative. Check out these tutorials. So here we go, gentlemen, the same procedure, but notice that here imported load, yes, insert body temperature or pressure. This means that you are gonna apply the pressure, but it will be as the same as the CFX solution. And here is the benefit from the CFX investigation to see the loads. So here the geometry also will be the same faces that we uh, have chosen. Okay, make it to select it faster. Because this pressure acts only on the blade, we're gonna select only the blades. Okay. And this. Okay. And here we go. So I'm gonna check this surface, and this surface we do not need it. We only need the pressure X on the blades. Okay, please be careful. So this is the geometry. Okay, and here the CFD, we're gonna select the R1 blade to import the pressure distribution from CFX here to here. Okay, so this is the imported pressure. Another thing, you have to the rotational velocity is gonna be 95,000 RPM to pi by 60 8901.17 and the axis. Okay, anti-clockwise, as notice that it's ramped from here to here. Okay, and you can change, I think, the step off. You can make it off or anything you can. Gentlemen, you have to cover this from the manual to know what you can do. Okay, we're gonna make it 1. Here's rotational velocity, and also we have to add fixed support threshold. Uh, the supports, fixed support, gonna be this and this, or you have to select exactly what is the fixed. You may, okay, 3 phases. So here fixed support, rotational velocity, but the pressure is not like what we did, but it is from the CFX solution. Again, you have to get the results what you need. Total deformation, stress equivalent, fatigue tool, life damage, safety factor. Also we can stress tool. Okay. Okay, hit solve. Notice that we did not import the temperature. It's okay now. Hit solve. Okay, here the mesh is being generated, and then it will start solving the solution. And here is the, well, I think that we have here a problem. Yes, in the mesh has to be fine. Generate mesh. Okay, solve. So I have to wait, please. Here's Dr. Delio simulations. It's very good channel for beginners. Okay. And here for model. So here is a statics analysis all again from mass stress and total deformation, and here's the, also you can make a transient thermal analysis like what I did on the PV panel cooling. In Kansas. Yes, this is my tutorial. You can check it out to see the steady state and transient analysis of thermal, and you can also use it like this paper to see temperature is applied and there is convection or something like this. The thermal to structure coupled analysis, also you can get the solution and transfer it, and here are the conditions and the fatigue and everything you need. Very interesting papers, very interesting research, and here we go. So this is the overall progress. And here we go, this is the solution without any temperature. This is the total deformation. Notice that is, I think it's good, is very high, because the structural steel is not appropriate for these loads. Notice the deformation. Okay. also the equivalent stress. And 28,908 megapascal. Okay. Here the stress is the maximum equivalent from 5 the megapascal, and here we have the very high, very high. So the cannot stand. Although they stand, the fatigue. This is the life cycles. The damage. Okay. And the safety factor. Notice that the parts that lower than 1 will get failure or have failure. Okay, it's lower than 1. Also can add safety factor, the stress too. This is the safety factor of the stress of the 0. Lower than 1 is not good for this material. Generally have to be sure that the safety factor is being more than 1. Okay. Okay, so it's okay now, and here is the imported pressure. The imported pressure in megapascal. Yes, this is in megapascal in the units. And also we can import another load, the body temperature. Okay, doesn't matter. And here for R1, this is the temperature of the blade of or the other R1. Okay, then it solve the temperature distribution of R1, the full R1 from CFX solution. And so the overall progress. Okay, and here we go again. So this is the imported temperature, as you know, 991. Open the results to check it out. It's a very high temperature. Here the maximum pressure 3.87 10 to the power 5 divided by 10 to 6. Okay, 3.13. So the pressure, yes, this is the maximum in megapascal, 387. It's like 3 4, and here is 3/8, okay. And here the temperature applied. So see, so this is in Kelvin, the maximum here 1.266 10 to the power 3 Kelvin, minus 273 is gonna be 993 Celsius. Okay, so this is the maximum. So this is the solution from the CFX, and is distributed here, and here are the results. The safety factor, notice that the safety factor, the majority of locations cannot withstand this pressure and temperature. So this material is terrible. Structural steel is terrible. And here the total deformation. Notice that the total deformation increased, I think, due to the thermal expansion. Also, the equivalent stress very high, very high. So the maximum is here. Okay, and the fatigue life and damage. Okay, and notice that here this these areas are in red, and the safety factor also tells us that the if it is lower than 1, gonna crack, and it cannot be a good solution. You have to get a high safety factor. Okay, exactly like this. Exactly like this is okay. Also, the last thing, you can make a chart, new chart between the objects, and here the total deformation. Okay, I think with time linear, again x-axis and y-axis, can type its the name, and time is x-axis. Okay, or you can make like this. Yeah, so the formation, and here the formation minimum or maximum, make it maximum. Time, do not display the time, omit the time. Yeah, here also you can make it equivalent stress. I think, but I'm not sure. You have to make the analysis before this. Here is to yeah, it's the chart, linear. Okay, you can check out Dr. Daliu's simulation, and he showed the chart, how to do the chart, but he did it using the analysis type, make it this time steps up to 10 to see the charts, okay, of the solutions you get. You can make many things here, like lines. Okay, also here is another solution. Yes. So, like I said, gentlemen, you can check out how to make charts. You have to select the two objects or any object, here the x-axis and here and the other axis, and to know here you can display or omit. Okay, to get the chart you need, but okay, it's not a problem now, so you have to try it by yourself. Check out more tutorials about the charts, how to make charts like this paper. Okay, can get this versus another thing, and also you can make probes. Can insert probe to measure anything you need. Okay, at a particular point. I showed this in details in the tutorial of the PV pen. Please check it out to see more information about the probes. Okay, gentlemen, I think that this is good until now. Another thing I have to say that there is another method for getting the mapped surface, or to make the mapped pressure by mapping to, this is the mapping, but by the commands. Using the commands, you can check out the aero mechanical. This you have to check it out. We may cover it in another tutorial in details. They use the command method to get the pressure map of the blade and then use it, but this is for the transient blade row solution. If you carry out a transient blade row solution and you want to get the unsteady pressure for this structural analysis, you have to I think you have to make it using the command, but I'm not sure. I'm gonna cover this later if allowance. So this method is unidirectional pressure mapping, CFD to mechanical APL. You can check it out from the website. I hope I cover it later. Okay, this. Thank you, gentlemen. I hope this tutorial be useful for you. Thank you very much for having patience. Wassalamu alaikum wa rahmatullahi ta'ala wa barakatuh.